Okay, today we start with 1D maps. Okay, remember what they were? 1D maps? Yes, exactly. We already encountered one 1D map, which was in this Rössler attractor, right? After, yeah. Also in Rössler you have 1D map, but also in the Lorentz one, right? Do you remember? We plotted z n versus z n plus 1, and there was this nice tent map, right? So now we will look into these things very closely, okay? So where they occur, they occur as a tool for analyzing differential equations, as we see in here, right? They occur as models of natural phenomena. In some scientific contexts, it is natural to regard time as discrete. This is the case in digital electronics, in parts of economics and finance theory, in impulsively driven mechanical systems, and in the study of certain animal populations where successive generations do not overlap. Okay, we will particularly talk about this one because you remember the logistic map, right? So we will look at that map. Okay, and finally, they have pedagogical power. Okay, they are simple examples of chaos and how chaos arises. Any questions so far? So, logistic map, and it's analyzed in detail in this influential review article by Robert May, who emphasized that even simple nonlinear maps could have very complicated dynamics. Okay, one of them is this logistic map. Basically, if you change some units, you arrive at this expression, which can be considered as, let's say, this year you have this many bugs. Okay, then what will be the number of bugs next year? Okay, could be a good example of that. And basically, the article ends memorably with an evangelical plea for the introduction of these difference equations into elementary mathematics courses so that students' intuitions may be enriched by seeing the wild things that simple nonlinear equations can do. Let's actually read those parts from this influential review, published in Nature, of course. In spite of the practical problems which remain, this is the conclusions part of the paper, okay? He says that the most important applications, however, may be pedagogical. We will see why it is so important, okay? But first, let's motivate about this paper. The elegant body of mathematical theory pertaining to linear systems like Fourier analysis, orthogonal function, and so on, and its successful application to many fundamental linear systems in the physical sciences tend to dominate even moderately advanced university courses in mathematics and theoretical physics. Do you agree with this? Yes? The mathematical intuition so developed ill-equips the students to confront the bizarre behavior exhibited by the simplest of the discrete nonlinear systems, such as the equation that I have just mentioned, okay? Yet such nonlinear systems are surely the rule, not the exception outside the physical sciences. So when you go outside the physical sciences, like if you go up to the level of biology, then these are not exceptions. These are usually the rule. Do you understand my point? Or his point? I would therefore urge that people be introduced to, say, equation 3 early in their mathematical education. This equation can be studied technologically by iterating it on a calculator or even by hand. Its study does not involve as much conceptual sophistication as does elementary calculus, etc. Not only in research, but also in the everyday world of politics and economics, we would all be better off if more people realized that simple nonlinear systems do not necessarily possess simple dynamical properties. Okay, he takes it to the upper level too. So basically, we have, let's think in general, okay? We have xn plus 1 equals f of xn, right? This kind of mapping. So what would be the fixed point of this equation? Remember, in differential equations like dx1 over dt equals fx1, we said that the fixed point is the one where this is 0, right? In this case, this is when x star, let's call it x star, is equal to fx star. That's our fixed point, right? So let's follow from here. Then x is a fixed point for if xn is x star, then xn plus 1 is also x star. Okay, hence the orbit remains at x star for all future iterations. Now, as we did with this linear stability analysis, now we will expand this xn around x star, okay? And you can see that if you expand it, so you have f of x star plus, let's call it some small value eta n, okay? And if you expand it, you have fx star, and then you have this one, right? The derivative of f at the x star, and then eta n. So basically, since this one is true, fx star equals x star, then this one takes care of this one, right? Do you understand? So you are left with this equation. You might say that this equation is no different than this equation, but it is very different because you can see that here eta n plus 1 equals to some number lambda times eta n. And you have this higher order term, but in the linearization we were ignoring it, right? So what if lambda is bigger than 1? What will happen? Mm-hmm. So if you go away from the fixed point even tiny bit, then it will explode, right? So the fixed point is not stable, right? So what if it is less than minus 1? Less than minus 1. It will also explode by oscillations, right? If it's between, so if lambda, magnitude of lambda is smaller than 1, then you have a stable fixed point. Do you all agree? Yes? So, very well. In the marginal case where this lambda is exactly equal to 1 or minus 1, then you need to consider these higher order terms. Okay? Okay, very good. So, for example, let's look at this example. Xn plus 1 equals xn squared. Okay? How can you plot it? This is xn, this is xn plus 1. It looks something like this, right? Do you agree? And it has a fixed point at 0, right? And it has also a fixed point at 1. This is where xn plus 1 is, this is the curve xn plus 1 equals xn. So this curve, which is xn squared, right, crosses this line in two places, right? This is one of them, this is the other one. So what about x star equals 0? Is it stable? So we just take the derivative of x squared, which is 2x. So at x equals 0, it is stable, right? It is less than 1 and bigger than minus 1 at x equals 0. What about x equals 1? If x equals 1, then 2x is equal to, right? Then that one is unstable. Okay, so if you start from x bigger than 1, then you will explode, right? If you start smaller than 1, then you go to and bigger than minus 1, then you are converged to x equals 0. Do you have any questions so far? Yes or no? Any questions?
Is it x bigger than 1 or x bigger than 1 over 2?
X bigger than 1.
So
just
we are checking the derivative, right? So the derivative is 2x.
The derivative, yes. The derivative is 2x, yes.
So we are checking if 2x is bigger or smaller than 1.
No, we are checking whether 2x at x equals 1 is bigger or smaller than 1. You understand? I mean, this is my fixed point. Are you sure it's okay?
I'm listening. And you were.
Okay. So I check the stability by looking at f prime x at x equals x star.
Okay, I see now.
Okay, good. Very good. I promise it will get much more fun in a moment. Okay. So let me mention these cobwebs. Okay. This is one way of analyzing these plots. For example, let's analyze the one that we have just mentioned. Oh, sorry. Something like this and something like this. So how can you iterate? What you can do is you can, let's say you start from xn, right? What is xn plus 1? You can go here, and if you go here, then that is the xn plus 1, right? Because this is the xn plus 1 curve. Then, so this is the xn plus 1. Do you agree? Then I go to this curve again, then I bounce back to this here, then this is xn plus 2. Do you see? If you don't see, please let me know. Everybody sees this? So this is a way of analyzing this plot. And for example, let's look at xn plus 1 equals sine xn. Then you, let's say if you start from here, you go like this, like this, like this, you bounce off and you reach x equals 0, right? What if xn equals to cosine, n plus 1 equals to cosine xn? What happens then? Here is the example. So you bounce off this curve, you go here, you go here. Now you reach this. If we zoom up there, you have this behavior. Do you agree? Yes? Again, converging. Any questions so far? No. Now let's come back to logistic map. Logistic map has this R here, a parameter. And do you remember what happened with, for example, Rössler attractor as we changed C? Do you remember what happened? It was like this, then it turned into this, then it turned into, I'm not sure if I'm drawing it well, this, as we changed C. Do you remember that? We weren't here. Oh, very good. So, Let's analyze this structure, okay? What if R equals to 2.8, for example? What will happen? So no matter where you start, like 0.3 bugs, 0.7 bugs, you understand what I mean by bugs, right? Like animals. Then the next year it will be this much, the next year this much. Eventually it will settle to some point, right? What if you increase R to 3.3? Do you see what happened? Now it reached at a period 2. So now it's many animals, less animals, many animals, less animals, many animals. You see? If you increase R even further, then you reach at period 4. Actually, let me show you some animations of this that people did. Okay, watch this one, okay? R is increasing. Don't watch this one, watch this one, okay? R is increasing and you will start getting period 2 in a moment. Do you see it? Yes? Then R increases and then this one turns into period 4. Did you see that? Yes? 8 and then after a while it's chaos. Okay? So how can we analyze this properly? What we can do is to open one of the codes that I wrote. Not this one. Yes. So let me tell you what I'm doing here. So I will change R starting from 0 to 4, okay? R will be changed from 0 to 4, okay? This n is, what should I call it? The number of points tried in R. Do you understand? Like R is separated into n points when you go from 0 to 4. Okay? And this is the number of iterations for each R. Okay? And then I will just set this one is a matrix that has like a size of n and m. This will correspond to history of population. Okay, each row was this one, right? Each row will be a history of animals corresponding to some parameter of R. Are you with me? Yes. Then, so I go from 1 to n. I set xn1 to 1 over 2. So I will always start with 1 over 2 population at the beginning. Then I start iterating. Okay. Let's start with 1 over 3. Later on, I realized that it's better. So I go from 1 to m minus 1, while xn m plus 1 find population in the next generation. Okay, and this one is start with 1/3 animals. Okay?
Just a leg or something.
Yeah. But you get what I mean, right? Because there are some redefinitions, like 1/3 million animals, something like that. Okay. And what this is doing, what this will do, can anyone say? Let's say I want to write something like this. So this will plot for each R value, plot the last 1024 iterations. Okay? Okay, let's just run this. Are you with me? Yes? Wow. Right? So you can see that until R is 1, we have just one fixed point, which is 0. All animals die, right? Then as R passes 1, you have this stable number of animals, right? The oscillations go and then they are fixed over here. What happens next? They start oscillating between two different values. Do you agree? Everybody? Then what happens next? It starts oscillating between four different values. Then 8, then 16, 32. And let's just check this one here. Do you see? It's very complicated. And right about here at 357 or so, you actually hit chaos. Because now you are 32, 64, it goes on. And you can see that as you approach this, the period doubling, the R parameter that you need to span for period doubling to occur gets smaller and smaller. Okay? So let's see what's happening here. Remember the period doublings. So we had started from 0 until reaching 1. We had this. Then at 3, we hit the first period doubling, right? Then we had this one. Then we had this one, etc. So what Feigenbaum realized is that if you look in very much detail when these occur, when these period doublings occur, then you will realize that, let's say this is the Rn plus 1, this is Rn, this is Rn minus 1. And let's take this limit as n goes to infinity, Rn minus 1, which is this length, divided by this length, actually approaches to a universal constant. It always approaches to this one. And it has nothing to do with other mathematical constants. Not that we know of. Like, it has nothing to do with E or pi or I. Okay? So it's a new universal constant that tells you how chaos is approached. Okay? So, good. And this plot is self-similar. For example, this is going from 3.4 to 4. But if I take a window over here, do you see where I took the window? And explore this part, you can see that it's the same as this plot, only flipped. Do you see it? So this goes from 3847 to 3857. Okay, very good. So I was actually planning to go into very much detail of this one, but we lost a lot of time. So just let me tell you that by the fixed point analysis that I just mentioned, you can show that certain points will be stable until you reach some R value, etc. Okay? I mean, at least, okay, let me tell you how this one appears. Like, you had until R equals 1, you have 0, right? But then this one appears. How that appears? Because as you increase R, before R equals 1, this one never crosses the xn plus 1 equals xn curve. It never crosses it. But after R is bigger than 1, you have this fixed this point over here. You understand? Yes? Okay. So let me show you two more things, at least. One of them is this one, okay? You can see this number here. This is the plot that I spent a lot of time to do. So here what I wanted to do is, let's plot the other one more time. You know, we had this one. This one. So what if I could rescale these parts in such a way that this one is more or less equal to this one, and it is more or less equal to this one, it is more or less equal to that one, etc. How can I achieve that? Well, I will not explain in too much detail, but what I'm doing here is that I go from, I start with R equals 2, then I keep adding smaller and smaller values, okay? So let me first plot it and then explain what is happening here after you do it. Basically, I'm plotting the logistic map in a rescaled fashion so that you can see that indeed all these bifurcations are occurring. So if you are adding in this particular fashion, then every 1,000 iterations will correspond to more or less to this one of these bifurcations. So every time you have 1,000 iterations, you hit a bifurcation. 1,000, you hit a bifurcation. So that tiny region that you go from 3.5 to 3.57, do you remember? Yes. These are all explored here. And you can see that there are this, so I will zoom out here. You can see that it's the same plot again. Zoom here. Same plot again. I did zoom. Okay, I promise I did zoom. Then I zoom here, the same plot. Zoom here, the same plot. Okay? And that is not the only fun that you get to see. Let's also do one more thing about it. Are you convinced that this is a super interesting, like, very complicated thing already? I mean, I mean, maybe understanding it when somebody explains is not complicated, but the system is simple, but it creates complicated stuff, right? So one of the things that we analyze, one of the ways to find whether there is chaos or not is to look at Liapunov exponent. Do you remember that? We mentioned it. So what was Liapunov exponent? Let's look over here. So if you start with x0, let's say you find x1, x2, x3, etc., right? What if you start with x0 plus delta x0, very tiny bit of change, okay? Then it will be carried to the other iterations, right? So remember, in the case of dynamical systems, we had these two paths that started the same, but then after a while they started to diverge from each other. Do you remember that? So we said that it can be explained in this way, right? So with an exponent, so you have an exponential divergence if lambda is positive, right? Do you remember that? So after doing some calculation, like here, some definitions and very nice properties of logistic map, or in general the 1D maps, you arrive at this formula for Liapunov exponent. It seems complicated, but really it isn't. So basically, to find the Liapunov exponent, you need to take the iterations, right? You have x0, x1, x2, and then evaluate the derivative of f at those points, and take the logarithm, take the absolute value, take the absolute value, then take the logarithm, then sum it all, then divide by the total number of iterations. And the more iterations you have, the more you approach to the value of lambda at that point. So what is f prime in our case? Anyone? What was f? R x 1 minus x, right? What is the derivative of this function? R minus? Yes, 2rx. Very good. Okay. So let me show you how this is implemented in the code. So while I'm going to iterate, you are familiar with this code more or less. I have something different here, okay? Set Liapunov exponent to 0, okay? Then I will add terms to L. Like this is the term over there in the expression. And you can see that this is the derivative, right? Rn minus, like R minus 2R times X. Do you agree? So now I will plot both of them in a single plot. And you will see that indeed Liapunov exponent, whenever it becomes positive, you have chaos. Okay? Wait for it. Yes, now you have the two plots together, and you can see that Liapunov exponent goes down, goes up, but never crosses 0, right? It actually gets suspiciously 0 whenever you have a bifurcation, right? By the way. But when you hit chaos, it actually goes positive. Like, remember we hit chaos around 3.57, and that's where Liapunov exponent goes positive. Okay, so you have this rigorous way of defining chaos, and it works. What about this window over here? you can see that there is a period 3 window that opens here. Did you see that? This one, 1, 2, 3. Then it goes. It also has its own bifurcation over here. Okay, like this. It goes like this and that. Okay. By the way, you can see that when you have this period 3, Liapunov exponent again goes to minus. Do you see it? Liapunov exponent was happily positive, and then when you hit period 3 window, it goes down to negative again. And then again, at the bifurcation points, the Liapunov exponent is 0. Do you have any questions? No? Okay, let's have a break at this point. Thank you all. So, let's actually summarize what we had so far, okay? I hope this summary will clear, and please ask questions. Ask any kind of questions to clear it out, okay? So we looked at this system, right? R times Rn plus 1 equals R times Xn 1 minus Xn. We realized that when R is somewhere here, then the period is 1. Like all oscillations converge to a single point. Like for R equals this one, that point is this one. For R equals this one, that point is this one. Then as we increased R, we hit the bifurcation where this one turned into this one. Do you agree? Yes? And then that one also doubled over here, and etc. So the question you just asked is, what do we mean by universality? Where is it? Why it is universal at all? So let's first define what do we mean by universality. We mean that this distance where the two bifurcations occurred, this one, and this one, the preceding bifurcation. If I take this length and divide it by this length, I will get something around 4.7. Okay. Then if I take this length and divide it with this length and divide it by this one, then I again get something around 4.7. And then if I do that one for the even tinier ones, I will still get 4. I mean, if I do it as I approach chaos, I will approach to this number. Okay. What do I do you have any questions so far? Yes.
This is only for this system, or
no, not. And we will see. We will not prove it, but I will just say it. There is another constant here that we didn't even touch, and that constant, let's not touch it at all. Okay, this is enough. So this universality was discovered by Feigenbaum, and let's look at the story behind it. Okay. So this is very rarely used. You should read, and this is like in terms of excitement. You definitely should read that one. Have you read Gleich's Chaos? It's a very good read. I also recommend it. Okay, the original technical papers of Feigenbaum published only after being, of course, rejected by other journals. These papers are fairly heavy reading. See these ones for more accessible exposition. Here is a capsule of history. Around 1975, Feigenbaum began to study periodic doubling in logistic map. First, he developed a complicated and now forgotten generating function theory to study Rn, the value of R where 2n cycles first appear. Let's skip some parts. Feigenbaum had time to guess where the next bifurcation would occur. He noticed a simple rule. The Rn converged geometrically with the distance between successive transitions shrinking by a constant factor of about whatever I just mentioned, he discovered. So let's see his recollections. I spent part of a day trying to fit the convergence rate value to this one, to the mathematical constants I knew, whether it's related to e, to pi, or whatever. The task was fruitless, save for the fact that it made the number memorable. So it's stuck in his head. At this point, I was reminded by Paul Stein that period doubling isn't a unique property of the quadratic map, but also occurs, for example, in this one, which is another plot that has a hump in it. Okay? So we are approaching that universality. However, my generating function theory rested heavily on the fact that the nonlinearity was simply quadratic and not transcendental. Accordingly, my interest in the problem waned. First. Perhaps a month later, I decided to compute Rn's in the transcendental case numerically. This problem was even slower to compute than the quadratic one. Again, it became apparent that the Rn's converged geometrically, and altogether amazingly, the convergence rate was the same number that I remembered by virtue of my efforts to fit it. So, what do we mean by universality? We mean that whatever plot that you can think of that would give these bifurcations, that would arise these bifurcations. Let me draw it here. So whatever function that has something like this will result in bifurcation for a certain kind of parameter, and this number 4.699 will be the same. And actually Feigenbaum used renormalization to prove that this is the case. Here the only important part is that this hump should be quadratic. It shouldn't be quartic around it. Like it shouldn't, I mean, you should have x squared terms for sure. If you have x to the 4 terms, do you understand my point? Then you get some different number. But almost all physical problems, all problems usually have this harmonic approximation, right? You usually have x squared. It's a very special case when you have x to the 4.
Can I ask something?
Yes.
So if we compare different humps with x to the 4, then would they also give out the same constant as well?
No. I mean, you mean a plot that has not quadratic hump, yes, but a 4th degree hump.
I know they are going to be different from 4.669.
Yes.
But if you compare them between themselves.
Do we still get a constant? Yes. That's also an important question. Yes. You do get a constant. I guess. Not sure, but that's a very good question. But it's not 4.699. Okay. So is it just this plot? What it has to do, for example, with, remember that we went from Rössler attractor or from Lorentz attractor to 1D maps, right? So do we get same kind of picture also in the dynamical systems? Do you understand my question? We already have seen that in the Rössler attractor we saw something like that, right? So I will demonstrate you how Rössler actually behaves as you change C. Let me remind you first of our last plot. I hope you remember this one. Rössler 1. Let's look at this one more time. Do you remember this one? Yes? So what happened here? The period would double, yes, like this. Then quadruple, then octuple, then the next one is I don't know what's 16. Okay, so let's do the following. Let's actually use these maximas of z. Do you remember Lorentz took the maximas of z and he had a map, right? Let's actually, this is what this program is doing. As the c is changing from, so I change c from 2.5 to 6, okay? In the meantime, I'm finding these extremums and finding these maximums. You remember us doing that? I hope you do. Then I will just plot, instead of this attractor, I will just plot the extremums. Okay? So let's watch it happen. While I'm increasing C, I have more or less something that can be considered a line, but then it doubles. Do you see it? It doubled. So you have a period 2 because you have going like this, right? So you have two z's at the extremums. Can you guess what will happen next? Yes, let's watch it. So my message here is that logistic map, although I couldn't show how elegant it is today, for sure, but logistic map is a good way to analyze chaos. And whatever you learn from the logistic map, you can apply to all kinds of places. Right now, we are applying it to dynamical systems, for example. If you calculate again the times it takes for the bifurcation to occur, you will see that it again decreases geometrically with the same exponent. And then you go do some experiments in chaotic systems with convection, etc. You actually get this number from experiments, the same number. It's the geometry of nature. That's the fundamental message here. Do you have anything to add at this point? Anything? Yes.
So the chaos is, like in simple words, is unpredictable behavior.
Yes.
Like you cannot predict.
Yes.
But can't we predict this behavior, like this bifurcation graph, this graph is increasing in the same manner, like its period is double, then quadruple?
Yes. So chaos is the thing that we call after these bifurcations are done. When you hit the end of those bifurcations, you have infinite period, right? Because it's 4 period, 8 period, 16 period. And in the meantime, the time it takes, the parameter space it takes to reach that one is getting shorter and shorter, right? So you can actually find, if you sum up geometric series, you get a finite value, right? So you get a finite value where chaos begins. So that's when you cannot cannot say what will happen next. But that's the beauty of it. You have this order and disorder together. You can see how disorder forms from order, or chaos forms from different kinds of bifurcations. I hope it's the answer to your question. So you can see that even here in the Rössler attractor, you have this 3-period window, right? So it's the same thing, a variation on a beautiful theme, right? Very good.